Good afternoon, everyone, and welcome to Chegg's live Stoichiometry Office Hours. It is so great to have you on, whether this is your first time or your 10th time joining these. I hope you learned something tonight and prepare for those finals that I know you guys have coming up. My name is Allison. I'm a student at the University of Louisville studying chemical engineering. I have been a TA for regular chemistry and nursing chemistry. I've also been a tutor for organic chemistry and nursing chemistry. And then I've been a private tutor for organic chemistry, regular chemistry, and calculus. So I love chemistry, love math. I am here tonight to teach you guys all that I can and hope that you guys do so good on those finals and that final homework you have coming up. So a little about how this session is going to run tonight. I've prepared some practice problems that we'll start with, and I'm going to ask you to actively participate during those. So if you have any ideas about how to solve the problem or a step that we need to take, or if you know the answer, I encourage you to type that in the chat of wherever you're streaming from. Actively participating is just going to help you learn better, and then it'll help me know if everyone's understanding what we're going over. I've also tried to kind of have a variety of different questions to ask, so it touches all those main stoichiometry subjects. And if you have any questions, this live stream is for you. So any questions you have, it could be a completely new problem that you went over in class or on your homework that you're not quite sure of, or it could be something about what I am writing. I encourage you to type that in the chat, and I would be happy to answer your question right here on the spot. So it is a learning tool for you guys. I dropped my pen on the floor, so let me grab that real quick. But let's get started. Again, it is so great to have all of you guys. So we want to convert for our first question 174.85 centigrams to kilograms. I'm going to do kind of a broad overview tonight because I want everyone to be nice and prepared for those finals. But basically, we have our base units for this problem is grams. And then below grams, we have centigrams, milligrams. I'm just going to pick the main ones. And then above grams, we have hectograms and kilograms. So 1 kilogram is 1,000 grams. 1 hectogram is 100 grams. A gram is just a gram. A centigram is 1/100th of a gram. And a milligram is 1/1000th of a gram. So these kilo, hecto, centi, milli, they all have the same meaning for any base unit. So our base units are meters, we have grams, liters. So 1 kiloliter is 1,000 liters. So that 1,000, that 100, 1/100th, 1/1000, the same for whatever base unit you use. So it's just a unit of measurement that can be universal depending on the base unit. So that's a little overview on our centigrams and kilograms and what we're kind of converting. And now let's get to actually solving the problem. So I always like to write what I start with. It's 174.85 centigrams, and I want to go to kilograms. So now that we kind of have this set up, we know what we're starting with, we know what we're ending with. It's your time to actively participate. I'm going to give you guys about 30 seconds to tell me what conversions we'll need. Hint, I already gave you guys the conversions you'll need. So find the conversions you need and type those in the chat so I can know that we're all understanding what's going on. About 15 more seconds. You guys got this. All right, 5, 4, 3, 2, 1. So we are going to need to go from centigrams to grams and then grams to kilograms. If you said either of those, you're absolutely correct. Basically, the reasoning from going to grams is it's that middle ground. As you see in those conversions we wrote on the left side, we don't really have an exact conversion from kilograms to centigrams. Everything's in reference to that grams. So that's why we're going to go from centigrams to grams and then from grams to kilograms. Hopefully that makes sense. Again, if you have any questions, let me know. I am here to help you. And then we just want to plug those numbers in. So we know 1 gram is 100 centigrams, which we have as that conversion just right here. And then we know 1 kilogram is 1,000 grams, which we have just in that conversion right here. Hopefully that's making sense. The reason that we have the grams on the top on the first conversion, grams on the bottom, is they're going to cancel. Same with these centigrams, and then we are left with our kilograms, which is what the problem asks for. So I'm going to now give you guys, let's do 30 seconds to put that in your calculator and let me know what you would get for the answer. So we're just going to put 174.85 divided by 100 divided by 1,000. All right. So the answer would be 0.0017485. Now we're going to take it a step further because you have those finals. Your teachers are going to be expecting high things from you. So my next question regarding this is, how would you put this into scientific method? You have 30 seconds. Put this value into scientific method starting now. Or not scientific method. Oh my goodness, it's been such a long day. Scientific notation. Put this number into scientific notation. Now you got 30 seconds. All right, about 15 more seconds. Put that 0.0017485 into scientific notation. All right, 3, 2, 1. If we put this into scientific notation, we're moving that decimal to where there's one non-zero number before it, which then we would get 1.7485, and then we're doing that times 10 to the negative 3. Negative because it's a super small number, and then of course we have to add our units. So our final answer for this problem is 1.7485 times 10 to the negative 3 kilograms. Hopefully that's making sense. It's kind of an easy question to get us started tonight, but again, if you're confused about anything, let me know. If you're just now joining my live stream, it is so great to have you. I encourage you, answer any questions you can that I ask. Ask any questions you have in your mind. I'm here to help you. So I want this session to be personalized to you. So don't hesitate to type your questions in the comments. All right. Now we're going to up it a little. We're going to bring in moles to our problem. We want to convert 34 kilograms to moles of sulfur. So there's going to be a few things we need for this, but I don't want to give as many hints as I gave in the first question. So I'm going to give y'all, again, 30 seconds, whatever you know about this problem, any of the conversions we're going to need, how you would set it up, let me know in the comment section or the chat. Got about 15 more seconds. 5, 4, 3, 2, 1. Okay, so we're going to need two conversions for this. First, we're going to need our kilogram to gram conversion. Let's do a new color. And we have that right up here actually in the previous problem, so it's already there for you guys. 1 kilogram is 1,000 grams. Now what we need is a moles of sulfur to grams. So you might be wondering, how do we get this grams to moles conversion? We need our molar mass. Molar mass can be found on the periodic table. So if you have your periodic table, now is the time to open that up and look at it. You can pull one up on your phone or if you have a paper copy. But basically, whatever number is with sulfur that has the decimal, that is going to be your molar mass. So the molar mass is the number in the sulfur box or whatever element box that has the decimal. So for this case, we know 1 mole of sulfur is 32.07 grams, or we say 32.07 grams per mole. That's your molar mass. Definitely make sure you know how to find molar mass because I guarantee you there's going to be a question about it or using it on your finals. So now let's convert this 34 kilograms to moles. So we start with that 34 And then, like I talked about earlier, we always have to go to that base unit, especially when we're converting from kilograms to moles. There's not a conversion from kilograms to moles unless you're really high up in chemical engineering, but I don't think any of us are that high up. So we need to go from kilograms to grams. So we're going to do kilograms to grams, and then we'll do a grams to moles. So grams of S to moles of S. We start with 34 kilograms. So now we're just going to plug those values in that we already found. We have 1 kilogram is 1,000 grams. 1 mole of S is 32.07 grams. And now is your time to shine. You've got 45 seconds. Put this in your calculator and let me know what you get. Got about 15 more seconds. Three, two, one. So I forgot to mention this, but the reason that we have this set up this way is because kilograms are going to cancel out and grams are going to cancel out. So we're left with moles, which is what we're looking for. So if we put all this in the calculator, if you said that the answer was 1,060.18 moles of sulfur, you are correct. Great job. Now I'm going to challenge you again because we need to know everything if we're going to succeed on these finals. Round this answer to the correct number of significant figures or significant digits. You probably heard it called both. So round this answer to the correct number of sig figs. And I'll write that up. So it's sig figs is what I call it. It's a fun little name. So you've got 30 seconds. Round that to the correct number of sig figs. And again, if you have any questions, let me know. I am here to help. All right, we got 5, 4, 3, 2, 1. So with these kinds of problems, it's pretty easy to get the correct number that we need because whatever the problem gives us, however many sig figs that has, so since the problem gives us 2 sig figs, that's what we need to round our answer to. So we would have 1,100 moles of S if we rounded it to correct significant figures. Hopefully that makes sense. Again, if it doesn't, I am here to help, so ask any questions you have. If you're just now joining, it is so great to have you. Thank you for coming to this live stream, and I hope it really helps you learn. All right, again, ask those questions. While we're waiting though, let's move on to the short, long, and spin configuration of gold. So this is a really fun one. You either love electron configurations or you hate them. There's like no in between, but I think once you get the hang of it, it's a really easy question to get right on a test. So we want to know the short, long, and spin configurations of gold. I'm going to give y'all 1 minute to figure out the long. That's what we're going to start with is the long configuration. Let's switch up our color again. So long configuration, y'all have got 1 minute to start. You're gonna need your periodic table hint if you don't know where to start. Have to pull up that periodic table. So 1 minute starting now. All right, about 30 more seconds. Tell me, what is that long electron configuration of gold? Gold is AU. If you were like, what's that random AU stand for? AU is gold. About 20 more seconds. You guys have got this. Remember, actively participating is the best way to learn or just check your learning. And I know everyone with finals coming up, it's very, very important to make sure you know it. All right, 5, 4, 3, 2, 1. So long electron configuration, I'm going to go through how I would find it. Everyone, if you want to follow along, look at your periodic table. So we start in that top row where hydrogen and helium are. That's the first row, so it is 1s, and there's 2 elements that represent 2 electrons. So hydrogen, helium. We put a 2 there. Now we go to our next row, and we are at lithium and beryllium. We're all the way on the left. That is the S columns. There's 2 elements representing 2 electrons. Second row, so 2s2. If you're confused how I'm getting any of these numbers, let me know and I'd be happy to walk through it slower. Then we're going all the way across the second row. We should be at boron, carbon, nitrogen, oxygen, fluorine, and neon. That is 6 elements, 6 electrons, second row. So we are at 2p6. We go down 1 row all the way to the left. We're at Na, which is sodium and magnesium. Third row, 2 elements, 2 electrons, 3s2. All the way to the right, we should be at aluminum, which is Al, silicone, phosphorus, sulfur, chlorine, and argon. Third row, the P rows, or the P columns, and there's 6 elements representing 6 electrons, so we're at 3p6. Now we are going to go down to the 4th row. All the way to the left, we're at K, which is potassium, and Ca, which is calcium. So we are on the 4th row, S columns, 2 elements, 2 electrons. Now, let's go to that middle column that's kind of long. We are at Sc, Ti, vanadium, chromium, and then that whole thing. So it's kind of different, but these are the D columns, and the D columns go back one. So we're going to start, it's going to be 3D. I don't know why they decided for it to go back one and be like the 3rd row, but that's the way it is. So definitely make sure you have that in your brain for your finals. There's 10 elements, and then that means there's 10 electrons represented. So 10 there. Then we go all the way to the right. We're at Ga, which is gallium. So that is the 4p6, 6 elements, 6 electrons represented. We are almost to gold. We go down. We are all the way to the left, and we are at rubidium and Sr, which I can't remember off the top of my head, strontium, which is the 5s2, 4d10. I'm going a little faster now that we know what all of those and how they're labeled. And then we're, of course, at 5p6. We are almost done, guys. Almost there. I know this is so long, but it's the best practice that you can possibly get. We are at cesium and barium, which is our 6s2. Now we hit a really fun one because we are at the F column. So the F columns are that little box at the bottom of the periodic table that's not connected to everything else, but it has a few weird symbols there. That's our F columns. So that goes down 2 levels. So we are at 4F, and then there's 14 elements representing 14 electrons. And now, finally, we are to our gold. We count. We're at 5D. We count over 9 elements to get to gold, so 9 electrons are represented. That is that's the long configuration of gold. I know, super long, super crazy, but great practice. So I know I put the spin configuration of gold, but that's like extremely cruel. So I'm not going to make us do the spin configuration of this one, but we can do the spin configuration of the next. But what I do want us to do for this problem is find the short configuration for gold. I'm going to give y'all now 30 seconds to find that short electron configuration for gold. Time starts now. Got about 15 more seconds by that short short electron configuration, not spin configuration. We're not doing that. Let's cross it out so we know we're not doing that. All right, 5, 4, 3, 2, 1. For short configurations, we go to the last noble gas that we passed. So noble gases are that last column on the periodic table: helium, neon, argon, krypton, xenon, radon. Those are all our noble gases. They have full electron shells. So our last noble gas we passed, if we go up one row and all the way to the right, is xenon. So we put Xe in brackets to kind of represent xenon as a placeholder. And actually, xenon represents all of this. That all of the stuff highlighted in purple is the electron configuration for xenon. Now what we need to do is put what we didn't highlight after our xenon placeholder. So we have 6s2, 4f14, and then 5d9. And that's all we have to do for our short electron configuration. If that doesn't make sense, let me know, type it in the chat, and I would be more than happy to help. If it does make sense, great, that is fantastic. And let's move on. Before we move on, though, I want to say it is so great to have you. Thank you for joining this live stream. I encourage you to check out the live streams we have for the rest of the week. This is our last week, I believe, of live streams, but I encourage you to check out that QR code so you don't miss those final live streams for the other classes. They offer organic chemistry, regular chemistry, calculus, algebra, anything you can think of. Check that QR code out and you can see all about the different live streams Chegg is offering. And again, don't be afraid to ask those questions. I'm here to help you learn. I want to personalize this live stream to you. So any questions you have, it could be homework question, something you went over in class. I encourage you to type that in the chat and I would answer that for you right now. But let's move on till we get some questions. We want to know the short, long, and spin configuration of calcium. So like our last problem, we are going to start with long. So you're going to get 1 minute to tell me the long configuration of calcium. Again, you're going to need that periodic table. So that's your hint. You're going to need that periodic table for this. You have about 45 seconds. So as a reminder, or if you're just now joining, we are finding that long electron configuration of calcium. And we have about 1 minute to do that, or now we're left with about 30 seconds. So start typing those answers, start getting them in. This is great practice for those finals coming up or those end of the year exams if you're still in high school. About 15 more seconds. Start typing those in the chat so that we can all check and make sure that we're all getting the right answers. All right, 5, 4, 3, 2, 1. Okay, so we all have those periodic tables pulled up. I'm going to go through this a little bit quicker. That way that we can keep moving on with problems. And we kind of already went over this. The main point of this problem is to do the spin configuration. But we start out, we're at 1s2, represented by that hydrogen and helium, then 2s2, represented by that lithium and beryllium, 2p6, represented by the boron, carbon, and all of those. Then we're at 3s2, represented by sodium and magnesium, 3p6, represented by aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Then we're at 4s2, which is potassium and calcium. And guess what? Calcium is what we want. So we are already done with that long electron configuration. That's great. That was much better than this super, super long one we did for cold. So that's great. Now I want you guys to find the short configuration. I'm going to give y'all a little less time because the short configuration is pretty easy once you know the long. So we have 30 seconds. Type what you think the short electron configuration is into the chat. Your time starts now. About 20 more seconds. Whatever you think that short electron configuration is, let me know. And if you have any questions, also let me know. I'd be more than happy to answer them for you. All right, 3, 2, 1. So First, we need to find our last noble gas, like we talked about in that problem. So find calcium on the periodic table, go up one row and all the way to the right, and you should be at argon. So I'm going to put argon in brackets. Perfect. Now, what I want to do is see what argon is represented by, and argon's represented by all of this. So what's highlighted in purple is the electron configuration for argon. Hello, SKTV, welcome. Any questions you have, let me know, and I'd be more than happy to help. And then after argon, we put 4s2 just to represent where that calcium is. But we use that argon as a placeholder, and then we have that 4s2. So now there's one type of electron configuration left for us to write, and that is our spin configurations. This one's kind of going to be hard to type out on the chat, so we're just going to work through this together. We have different principles that teach us how to write the spin configuration. We have the off-ball principle, the Pauli exclusion principle. All these tell us how we write our arrows. And if you're very confused about what is this girl talking about, arrows, spin configurations, off-ball, this is how electrons work. They operate in different spins in different directions to stay orbited around the nucleus. So the way that we do this, I'm going to write out all of our different subshells that we wrote in our long configuration. All right, so we have all of those wrote out, and now we're going to do up and down arrows. So our S subshells have one orbital that can hold 2 electrons. So all of our S, I'm going to put one line. Now, our p orbitals have 3 subshells that can each hold 2 electrons. So I'm going to represent these 3 subshells by 3 lines. If you get lost, let me know. We can do some more practice regarding this. All right, now what I'm going to do is each of these subshells is going to get an up and down arrow until I go to get to calcium. So we have an up arrow, down arrow, up arrow, down arrow. This is the off-ball principle. All arrows have to go up before they can go down. This isn't really important in this instant, but if you have like something that ends at like 2p4, you'll have to know that all arrows get up arrows before they get down. And then we have 3s2, up and down arrow, up, up, up. This is a pretty easy one because we end on an even number, so we know that we're going to have all up and down arrows in every single subshell. But that is the spin configuration. Hopefully that makes sense. If it doesn't, let me know, and I'd be happy to explain it in more detail. If you're just now joining the live stream, it's so great to have you. My name's Allison. I encourage you to ask any questions you have throughout the live stream so that I can help you prepare for those finals, prepare for those exams that are ending your year, and that final homework. So let me know. Our next question is, what's the limiting reactant if I start with 18 grams of each, which is barium nitrate and sodium chloride? There's a few different steps we're going to need for this, but the first thing is we need a balanced equation. We have an incomplete equation that's not balanced. So I'm going to give y'all 1 minute to not only complete this equation, but also balance it. Your time starts now. All right, we've got about 45 more seconds. So again, complete that chemical equation and balance it. It doesn't have products right now, so figure out the products and balance the chemical equation. If you need any help or you have any questions about how to do this, let me know. We have about 15 more seconds. So anything you know about how to balance this chemical equation, let me know. All right, 4, 3, 2, 1. So the way we're going to balance this is our Cation goes with an anion. Cation has positive charge and are found on the left side of the periodic table. Anions have negative charges and are found on the right side. So barium's our cation. It's going to bond with chlorine, which is our anion, and going to form BaCl2. That's because barium has a 2 plus charge while Cl only has a 1 minus. So we need 2 chlorines to actually cancel out that plus charge of the barium. Now for the NO3s and the NAs, that anion NO3 is going to bond with the cation Na, and we're going to get plus NaNO3. Now that we have that chemical equation complete, if you said the barium chloride and sodium nitrate, you are doing great. You're getting so prepared for those finals. So now we need to balance it. So we have 1 barium over here, 1 barium over here, 2 nitrates over here, but we only have 1 nitrate over here, so we need to add a 2. We have 1 NaCl, or we have 1 Na, but we have 2 now over here, so we need to put a 2 there. And we have 2 Cl's and 2 Cl's. So now let's do one final check to make sure that everything's balanced. 1 Ba, 1 Ba. 2 NO3s, 2 NO3s, 2 NAs, 2 NAs, 2 Cl's, 2 Cl's. Yay, it is nice and balanced. And now we are actually ready to solve the limiting reactant problem. So I'm going to give y'all about 1 minute to figure out anything you can about how we would solve this problem and figure out what the limiting reactant is. So any conversions you know, steps you would take, let me know in the chats. And yeah, you've got 1 minute starting now. About 45 more seconds. About 30 more seconds. So figure out any steps or conversion factors that you'll need to find the limiting reactant if you start with 18 grams of each reactant. All right, 5, 4, 3, 2, 1. So we are going to start by just putting 18 grams of barium nitrate and 18 grams of NaCl because that's what the problem gives us, so that's what we start with. Whatever the problem gives is what you start with. Now, the way that we go about solving limiting reactants, well, first, let's do a refresher of what a limiting reactant actually is. So a limiting reactant right here is the reactant that limits product creation. So it's the reactant that limits product creation. So to figure out what reactant is going to limit product creation, we have to figure out how much product that reactant creates. So we are basically going to go from grams of these reactants to moles of these products, and we're going to pick one product. I'm going to pick BaCl2 just because it's the first one. We're going to go to moles of that product to figure out which of these creates less product. So whichever is less moles is going to be less of our, whichever creates less moles is going to be our limiting reactant. Keep that in mind because I'm going to ask you again after we actually do the math for this problem to tell me what the limiting reactant is. So let's go from grams of each of these. So grams of BaNO3 to grams of NaCl, 2 moles of NaCl, moles of BaNO3 2, so barium nitrate. Now, of course, I had to make sure we have those extra challenge problems or we're getting everything tested. So the part to this that's fun is we need to find the molar mass for barium nitrate and sodium chloride. So molar mass of BaNO3, and what's the other one? NaCl. I'm going to give y'all 1 minute to figure out this molar mass, and then I'm going to start working. But I want you to figure out both of these molar masses. So you're going to need your periodic table, you're going to need those decimal numbers we talked about earlier, and you're going to need a calculator to add up all the values. So your 1 minute starts now, and then I'll join in and start working. And if you have any questions while you're figuring out the molar mass, don't be afraid to type it in the chat, and I'd be more than happy to help you or go over it in more detail. We can do more examples if we need to, or we can do better explanations, so just let me know. All right, about 25 more seconds. So whatever you need, if you're getting an answer, start typing that in the chat so that we can check our answers together. The best way to learn is to attempt problems. That's what at least all my professors tell me. So I assume if all of them say it, it has to be true. All right, we've got 5, 4, 3, 2, and 1. So the way I'd go about solving this is I'm going to say how much of each element I have in each problem. So I have 1 Ba, 2 Ns, and 6 Os. Ba, let me find that molar mass because I'm going to need it, and I don't know it off the top of my brain. Barium has a molar mass of 137.33 grams per mole. We multiply it by an imaginary 1 because there's 1 Ba, so we don't really do anything. Nitrogen is 14.01 grams per mole, which we multiply by 2, and we get 28.02. Then we have 16 grams per mole times 6 O's, so that would be 96. And then we're just going to add all of these together. So let's put them in our calculator. 137.33 plus 28.02 plus 96. If you got 261.35 grams per mole, whoa, wrong pen, 261.35 G per mole for that barium nitrate. You are absolutely correct. Great job. Give yourself a high five. Now for sodium chloride, we have Na, which is 22.99, and Cl, which is 35.45, and we add them. So let's put that in a calculator. 58.44. If you got that, give yourself a high five. So those are our 2 molar masses. We're going to need them to solve the problem. So let's put, we said barium nitrate was 261.35 grams per 1 mole. And then we have that 58.44 grams per 1 mole of sodium chloride. Hopefully that's making sense to everyone. If not, let me know. Then our final step is we want to go from those reactants to our moles of barium chloride. So I'm going to put moles of BaCl, or moles of BaNO3 on the bottom, and moles of BaCl2 on the top, moles of NaCl, moles of BaCl2. Then we just need those conversions. So you might be asking, where do we get those conversions? We get them from that chemical equation that we balanced earlier. So we just find the coefficient to the problem. So we find the coefficient to the compound. So BaNO3 has a coefficient of an imaginary 1. BaCl2 has a coefficient of an imaginary 1. And then NaCl has a coefficient of a 2. So let's write those all in. 2, 1, 1, 1. Now, we're ready to do some math. So let's put these in the calculator. I'm going to give y'all 1 minute to put both of them in the calculator and check your answer. I'm going to write them on the board as I solve them. So your 1 minute starts now. All right, you've got about 30 more or 20 more seconds. I do now have those answers on the screen. So when you solve them or if you get stuck, you can look up and see what the answer should be. Got about 5 more seconds. 3, 2, 1. All right. So we started with that 18 grams of barium nitrate. We divided by that molar mass at 261.35, and then we multiplied by like 1, and we should have got 0.06887 moles of BaCl2 were created from the barium nitrate. Then, if we go to the bottom, we started with that 18 grams. We divided by the molar mass of 58.44 grams, and we divided by 2 moles of NaCl. We got 0.154 moles. And now, I told you I was going to ask you this, so hopefully you were paying attention. What is the limiting reactant? Is the limiting reactant barium nitrate or sodium chloride? You have 20 seconds. Let me know in the chat if that limiting reactant is barium nitrate or sodium chloride. About 15 more seconds. Which one of those is that limiting reactant? Let me know. If you get it right, you get a virtual high five, but I have to know about it to give you the high five. All right, 3, 2, 1. The limiting reactant, of course, is our barium nitrate. Why is that, you might ask? It's because it creates less product. So our barium nitrate creates less product than our sodium chloride. Therefore, it is the limiting reactant. So if I were to ask you how much product can we create, the answer would be 0.06887 moles, because we can't create more than that limiting reactant will allow us. That is a question that your teacher will use to stump you. And you would think, oh, I want to create more, I'll choose 0.154, but you actually have to find limiting reactant because you can't create more than what your limiting reactant allows. So as you go into finals, remember that, be super important, and it might get you some points on a test. All right. So we are a little over 2/3 of the way through our live stream. We're coming to the final minutes of this live stream. So I'm going to encourage you, any questions you have, anything you're not sure of, this is your time to study and practice before those finals, those end of the year tests, and those final homeworks. So any questions you have, homework questions, questions you went over in class, hypothetical questions, let me know in the chat. I'd be more than happy to help. I want to use these last minutes to help you. Also, now is a good time to call out that QR code we have in the top left or right. I don't know if the screen is split for you guys, but that QR code in the top left has all of our live stream office hours for the rest of the week. So we have calculus, organic chemistry, regular chemistry, algebra. I encourage you to check it out to see those remaining live streams and get that help that you need so that you can do so good to end the semester and the school year. All right, while we're waiting for some of those questions, let's move on. We want to know what the excess reactant and theoretical yield is if you start with 12 grams of each reactant. All right, another limiting reactant problem. We're going to go through this one a little bit quicker. You have 1 minute to balance the equation and figure out the products. Time starts now. All right, remember we're balancing the equation and figuring out the products. Got about 20 more seconds. All right, 5, 4, 3, 2, 1. Another trick, because I wanted to introduce a new skill. This right here is a combustion reaction. Combustion reactions involve carbons, hydrogens, and oxygens. They always form carbon dioxide and water. So I'm sure if you're in like general chem, you'll definitely see a problem like this. So now we want to balance it. Combustion reactions are probably the most difficult type of reaction to balance just because they aren't as straightforward as other reactions, but I think we've got it. So we have 4 C's over here. I'm going to put a coefficient of 4 there. we have 10 H's. We only have 2 H's here, so we're going to put a coefficient of 5. And now in total, we have 13 O's, and we need to make this a 13 on the left. So we'll put 6.5. And then to make those all whole numbers, you're going to multiply everything by 2. So 2C4H10 plus 13O2 yields 8CO2 plus 10H2O. So hopefully that made sense. If you have any questions about how I balance that, let me know. Or now I'm going to ask you to set up the problem. Again, you have 1 minute. Tell me anything you know about how we would set up and solve this problem. Your time starts now. All right, 40 more seconds. Anything you know about this problem, conversion factors, molar masses that we're going to need to know, let me know in the chat. 25 more seconds. You have got this. Let me know anything you can think of. All right, 5, 4, 3, 2, 1. So we're going to start with what we're given, which is 12 grams of each reactant. So 12 G's of C4H10, 12 G's of O2. Let me write that a little lower so we have some space. So then we're going to go to our moles. I'm moving through this a little quicker just so because we already did it, but it's still good practice. So this is probably about the speed that your teacher would want you to do on a test. And then we're going to go from moles of C4H10. I'm going to choose to go to moles of CO2 because, again, that is our last. That's the first thing in our products. Moles of O2 to moles of CO2. And now let's add those numbers. Let's add those numbers for the conversions in. So 1 mole of C4H10. Let's give you 30 seconds to figure out the molar mass of C4H10 and O2. 30 seconds start now. We need those molar masses for the problem. C4H10, fun fact, if you are about to go into organic chemistry, C4H10 is isobutane. So if you don't learn anything tonight, at least you know how to name something for organic chemistry. All right, so your 30 seconds is up. We have 1 mole of C4H10 is 58.12 grams of C4H10. 1 mole of O2 is 32 grams of O2. The way I got that, C4H10, 4 times the molar mass of C plus 10 times the molar mass of H. Added those together. O2, just 2 times the molar mass of H. Now, for our mole to mole conversions, again, we're going to use those coefficients. So CO2 has 8 and C4H10 has 2. And then moles of O2 is 13. Okay, now you guys have 1 minute. Figure out what the excess reactant is and solve both of these stoichiometry problems. Your time starts now. When you're done, if you want to check your answer, it'll be up on the board. First answer is up. Second answer is up. All right, so now we need that excess reactant, and that excess reactant, of course, is what creates more CO2, so C4H10 is our excess reactant. And now we need our theoretical yield. Our theoretical yield is whatever the limiting reactant creates, so our theoretical yield would be 0.2308 moles of carbon dioxide. So that was a quick run through of excess reactants and theoretical yields, but again, super important to understand for finals. So if you have any questions about that, let me know. I would be more than happy to help. We are to our last 10 minutes of this live stream. So I'm going to encourage you, ask those final questions so that you can learn better and we can all learn together. I can help you as you need. But until we get a question, let's move on. So we want to know the equilibrium concentration of the following if I start with 4 molars of each reactant. So first we need to figure out what N2 plus O2 will create. I'm not going to give you all a whole lot of time to work on this one on your own because we are a little crunched for time and I want to have time to answer questions as they come through. So I'm going to put, we know N2 plus O2, it's a little weird, but it's going to yield N2O. So now we need to balance it. 2 N's, 1 O, but 2 O, so we put a 2 there and a 2 there. Final check, 4 N's on the left, 4 N's on the right, 2 O's on the left, 2 O's on the right. That's the balance equation. Hopefully that makes sense. Now we want to do our ICE table. So I, C, and E. I is initial. The problem tells us we initially start with 4 molarities of each. Molarity is just moles over liters. We start with 0 products. And then we need the change. So we use those coefficients as the change. So we would subtract 2x, subtract x, add 2x. Reactants get subtracted because you can think reactants are going away to create products. So the change is going to be reactants disappearing. Products get added because you can think those products are appearing. So product is being created, we add product. And then that 2 just comes from the coefficients of the balanced chemical equation. And then for our equilibrium, we just bring these all down. So 4 minus 2x, 4 minus x, and then 2x. And our K equation is going to be reactants. So the concentration of reactants over the concentration of products. So K equals 4 minus 2x squared times 4 minus x squared. And actually, for the purpose of, it's just 4 minus x, my bad. Because since we don't have that 2 coefficient, we don't square it. And then over 2x. So now let's multiply that out. Let's solve. We're going to get 16 plus 4x squared. Whoops. We're going to get 4 minus 2x times 4 minus 2x times 4 minus x over 2x. All right, now let's multiply. So 4 times 4 is 16 minus 8x plus 4x squared. Multiplying all of these by 4 minus x. Oh, and I forgot to put what k is equal to, but k is equal to 1. And that's all over 2x. And that is equal to 1, which is k. Now we multiply one more time. We get 64 minus 32 minus 64x. I'm going to go ahead and combine those like terms. Plus 16x squared. And then minus 16x plus 16x squared plus 4x or minus 4x cubed. And then all over 2x. So let's combine like terms. Our 64s will cancel out. We'll be left with, that was a 16x, oops. We'll be left with 32x squared minus 16x minus 4x cubed over 2 equals 1 over 2x. Oh my goodness, I'm not even copying everything over. All right, that was some quick math. but we're going to keep powering through so that we can get this problem done in time for the live stream. If you have any questions about the algebra, though, let me know, and I'd be happy to go over whatever parts we're struggling with in some more detail. Now, we have an x that we can cancel out of everything on the left side, so we have minus 4x squared plus 32x minus 16 over 2 equals 1, and then we can divide everything by 2. So negative 2x squared plus 16x minus 8 equals 1, and then we can subtract that 1 over. Minus 2x squared plus 16x minus 9 equals 0. Now we can do the quadratic formula. So if you remember the quadratic formula, it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. There's a song if you can't remember it, and once you hear the song 2 or 3 times, you'll never forget it. But we have x equals negative b, so this is a, this is b, this is c, negative b, plus or minus the square root, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative 16 plus or minus, let's put that in the calculator. It's 256 minus 72 over negative 4. Then the square root of 184 is 13.6 over negative 4. And then we want to pick whatever is going to give us an answer that will give us a logical answer to plug into the equilibrium. So since we're doing a 4 minus x, subtracting this will give us an answer greater than 4. So we want to add it. So we do negative 6. We're going to pick, my pen real quick. We're going to pick the add option, negative 16. Whoops. Okay, there we go. Negative 16 plus 13.6 over negative 4. We picked the add option because if we picked the minus option, we get an answer for equilibrium values that would be negative, and you can't have negative concentrations at equilibrium. So we would do 13.6 minus 16 divided by negative 4, and we would get 0.6. So now let's go up here, and to find those final equilibrium concentrations, which is what this asks for, we're going to plug in x equals 0.6 into each of these equations. So now I'm going to give you all the opportunity to plug that value in. You're going to have about 1 minute, plug it in, and let me know what you get. I will be writing them as we go, so you can check your answers as you solve for each of them. All right, you got about 30 more seconds, but again, if you want to check those answers, I have them up. About 5 more seconds. 3, 2, 1. So if you plugged your X value in correctly, you should get 2.8 molars for nitrogen, 3.4 molars for oxygen, and 1.2 molars for that dinitrogen oxide. A cool thing about that, a way you can check yourself, is because the conservation of mass, what the mass that you start with should equal the mass that you end up with. Or wait, I'm being silly. Never mind, ignore that. This is molarity, not mass. But these are the correct values that you should have got. If you have any final questions, feel free to ask. But we are about at the end of our time of the live stream. Hopefully this live stream helped you to get ready for those finals and end of the year tests. We hope that you guys have an amazing summer. This is our last Stoichiometry office hour for this school year. So it was great to have you join tonight. Thank you, Chegg, for putting these live stream office hours together. And go have a great summer. Have a great